Okay, so thus far our speakers have all talked about current robotic space missions, and all of the bodies they study were first observed by ground-based and space-based telescopes. Our next speaker will describe how such observatories are being used to expand our reach beyond our own solar system to pave the way for robotic missions that may take place far into humanity's future. Susan Lederer is a planetary and space scientist at the Johnson Space Center. Her research is in both orbital debris and planetary science, with an emphasis on comets and asteroids. But Sue also studies exoplanets, which is why we invited her today. And she's been involved with an international team of scientists who discovered 7 Earth-like planets around the ultra-cool dwarf star TRAPPIST-1. Sue.
Forward, backward.
That goes forward, and I think that's the laser.
Great. Hi, it's an honor to be here to speak to all of you today, and even more fun that we could discover a planetary system around a very small, very cool star that allows us to publish nature papers with the word ultra cool in the title. So it's been a lot of fun for us. It is a very international team that was led by a group of Belgian astronomers, and this is the point where I explained to you where the name TRAPPIST came from. TRAPPIST stands for the Transiting Planet and Planetesimal Small Telescope, which may sound like a stretch, but then you must realize that these are Belgian astronomers that are leading this, and these Belgian astronomers are particular fans of the Belgian beer that is brewed by the Trappist monks. So in fact, it is no accident that that is where the TRAPPIST name came from. The other thing to note is this was designed to look for transiting planets around other stars. And for 5 years, they looked and looked and looked and got nothing, nothing, nothing. The -1 indicates that it was the very first system that they discovered with their TRAPPIST telescope. So they just happened to get either very lucky or very good to get such an amazing system as their very first discovered planetary system. So it's the TRAPPIST-1 system. They had a very small telescope it's about a 0.6 meter diameter telescope using visible light. And with looking at transiting planets in visible light, there's also the possibility that you might be seeing star spots or flares or some other sort of stellar activity that mimics the same sort of signature. So as soon as they discovered the possibility of the transit, they thought, okay, we need more data from other telescopes, which is where I entered into the picture. They said, hey, we know that you have this great 3.8 meter telescope. It's all infrared on the top of Mauna Kea. This was under a NASA contract at the time. So do you think there's any possibility that NASA would allow us to use this telescope? Well, like all good planetary scientists, my answer was, that's above my pay grade. So I went to the director and requested director's discretionary time. That was part of the time that the director, in fact, has the discretion to determine whether or not to use the telescope. And thankfully, he said, yes, you can use the telescope. And we then helped with the very initial discovery of the system. The initial discovery was only 3 planets. We did a very good job at estimating the periods of the 2 innermost planets. And for those of you who are wondering where TRAPPIST-A might be in that system, TRAPPIST-A is in fact the star. So the first planet is TRAPPIST-B. And at the time, we knew that there was something else going on in the system, but had only gotten enough ground-based data with, in fact, 4 different ground-based telescopes at the time to be able to determine the periods of the 2 innermost planets. We also note that the point of looking at transits of planets going by the front of the star, instead of directly imaging the planets themselves, is very much because directly imaging planets is very, very difficult. So imagine a firefly, and this firefly is probably the brightest firefly that I've ever seen in the universe. But it's like, imagine trying to image a firefly in front of a 1,000,000 candlewatt spotlight. It's extremely difficult. So instead of imaging the planets directly, very predominantly we're looking for other signals that indicate that there is a planet around your system. So this shows you, for example, why it is easier to determine whether or not there are planets around other stars that are much smaller. If you're looking at planets around other solar-like stars, and even the sun is considered a yellow dwarf star, but if you have an Earth-sized planet in front of the sun, you're looking at blocking about 1/100th of 1% of the light. those of you who have ever done any kind of science, you know that there is noise in your data, and 1/100th of 1% can often be simply the noise value. So it's really, really difficult to determine whether or not there are transits going in front of sun-like stars. TRAPPIST itself is much, much smaller. It's only 8% the mass of the sun, 12% the size. So that means that if you have a transit of an Earth-sized planet in front of that, you're looking at more like 0.5 to 1%. So it's easier to detect transits in front of something that's this small. So that's one of the big benefits. It's also only 40 light years away. That's 12 parsecs for those of you who speak astronomer. And while 40 light years might sound like a far distance to those who are not very familiar with the sizes of the universe, our galaxy is 100,000 light years across, and our universe, 13.8 billion light years across. So 40 is really just in our solar neighborhood. It's really, really close by, and also then allows us to be able to get detections with much better signal and much better assurity of what we're looking at. So what does the signal of an exoplanet look like? So the data themselves look like this. And as I'm going along, I'm going to show you all of the interesting information that we can gather just by looking at that. And if you're not amazed at the clever nature of astronomers by the time you're done, I want you to come and tell me what you think is clever, because it's really, I think, amazing what the team has done. And the team is very strong and very, very good at what they do. So that's what transits typically look like. And we got data in September of 2015 while the star was still a nighttime object. Well, by January, it became a daytime object. And we got one very strange set of transits. And you see that transit in December back in 2015. And we all sort of puzzled over this. What could this be? This doesn't look like a typical transit. It's obviously more than one object. Is it maybe 2 planets going by? 3 planets going by, maybe a double planet in the system. There might be a double planet and a moon. What could this possibly be? So we tried at that point to gather as much data as we could to try to tease out of the dozens of possible periods that could create this, what was causing this. And the answer was none of the possible periods that we were able to see with our telescopes on the ground confirmed what these periods possibly could have been. Well, any of you who are astronomers and who are trying to take data with a ground-based telescope knows that we have a couple of annoyances, one of those being daytime. Yes, it's true that sometimes you're not looking at the right portion of the time, but there's also weather that comes into play. So, of course, the team, looking at this, we've got 4 telescopes that we're using at this point, looks at this and says, we need more data. What kind of data do we need? Well, we really need data that's constant for as long of a time period as we could possibly have. Looking at it where you don't have to worry about weather and you don't have to worry about daytime getting into your way. Well, everybody knows the answer to that. Use a space-based telescope. Space-based telescopes are very highly sought after time. So we started talking, the PI said, I think we should ask for Spitzer Space Telescope time. It's up in space, it's infrared, it's perfectly suited, and I think that we should monitor this for a long time. So when you ask for Spitzer Space Telescope time, you normally ask for 10 hours, 50 hours, 100, maybe a couple of hundred if you have a really important system that you're looking at. So I said, okay, well, how much time do you think we should ask for? And he said, I think we should ask for 1,000 hours. To which I said, all right, well, you're crazy. There's no way they're going to give us 1,000 hours of telescope time. He said, yes, but this is such an important system, and there's a possibility of planets in here being right in the zone where you could have liquid water and potential for life to form. This is so important. We should ask for 1,000 hours. I said, okay, well, I recommend that you actually go talk to the people at Spitzer and let them tell you how crazy this idea is. So we contacted Spitzer, Sean Carey at the Spitzer Science Center. And Sean Carey not only said, yes, I encourage you to apply for Spitzer time, but oh, by the way, do you need a collaborator? So we then gained more help from the NASA side working on this project, which we noted is very international. Of the 15 of us who were part of the initial discovery, I think I was the only one on the US side. Of the 30 to 32 on the follow-up big discovery of the 7 planets, about half a dozen from the US, the rest very international. So it's been a really interesting project working with people who are native French speakers, trying to communicate that. So that's been a lot of fun. So we did go, we asked for Spitzer time. The first 500 hours we used continuous with the other 500 in spare to look at more detailed observations. And during this time, you can see that there are some gaps when the telescope has to download data. And it was September of 2016 that we started this 20-day campaign. And by October, as soon as the data were released to the team, we analyzed it. And they said, okay, sitting next to somebody during a conference, how many planets do you think they found? I said, I think they found at least 5. He said, no, there's 7. So that was super exciting because this many planets in a planetary system hadn't been discovered before like this. So our planetary system then grew from a system of 3 to a system of 7. The color coding that you see there is very intentional. The red indicates that it's too warm to have liquid water facing the sun. The blue indicates that we're outside of the habitable zone. It's that green area where you can have liquid water sitting on the surface. E, F, and G are the ones that are typically referred to as the habitable zone planets. But if you get a little bit more liberal, there's some possibility that D might be part of that as well. So that's our full planetary system. But of course, we only got one observation of that outermost planet. So the team said, well, we obviously need more data. And we need more data from a space telescope, right? And Kepler is perfectly designed as a space telescope to look for transits of other stars. So we then put in a proposal asking for Kepler Space Telescope time and got 79 days. But the caveat to us getting 79 days was that that data was released to the entire public all at the same time. So our team was geared up with all of the tools that we needed so that when that data was released at about noon on a Tuesday, people feverishly worked on getting all the data reduced, figuring out what was going on, what was the period of that outer planet. And within 60 hours and 500 emails later, we submitted a paper on that Friday with our results. So that's what you have to do. And I don't know if any of you have ever published a paper in Nature before, but to say it takes longer than 60 hours in a general sense, I think is a pretty fair thing to say. So we managed to do that. It's an incredible team. So what kind of data then, what kind of characteristics can we get? Well, from the light curves, we can estimate, if we know the combination of their period, their distance away, from looking at the depth, what are the sizes, the radii of the planets? Also, how long that transit lasts and where it falls, you can figure out the orbital periods and distances to the star. And then from that, knowing how bright this star is and where they are with respect to the star, you can say whether or not they're in the habitable zone. In addition, when you look at the data, sometimes the transits happen a little sooner or a little later than when you expect. So this is called transit timing variations. So if you have 7 planets, all with distances and sizes and all the possible different periods that you could put in, and a big cluster of computers to look at all of those possible combinations, you can determine what the masses of the planets are. So now that you've got masses and you've got sizes, you can also determine densities, and that's why we know that they are terrestrial planets in nature, rocky bodies. So we have a lot of great characteristics. I want you to note that we have no idea what the surfaces of the planets look like. This is an artist's conception with a lot of the information. And within the first 2 weeks, 3.2 billion Webb hits on this system alone. And I was most excited about the little Google Doodle because I had known about the planets prior to that. So it was a lot of fun. And of course, everybody says, well, what's the next step? And the next step is, of course, we need more data. With a space telescope, preferably bigger in size and with infrared wavelengths, guess what telescope is perfectly designed for that? The James Webb Telescope, which is right here at Johnson Space Center, being tested right now. Just saw it 2 days ago. It's an amazing view. We can get what's called transmission spectroscopy of the atmosphere of the planets. This is supposed to be one of the initial targets for James Webb, and you can see some of the key molecules that would be indicative of life existing: water, ozone, methane, and carbon dioxide. All of those that you see there are really good indicators that there could potentially be life. So this might maybe be the very first system ever that we might be able to say, yes, life truly exists outside of our solar system. So super exciting for all of us. With that, I'll finish and just let you watch the little video of what we imagine potentially the surfaces could be like, noting that if all of these planets are in resonance with each other and each set of 3 are in resonance, it's possible that the same face is always pointing towards the planet. So that terminator edge could be a really good place, as you see in this image right here, for liquid water if you have an atmosphere to exist on some of the planets, even outside, slightly outside of the habitable zone or subsurface. So with that, I thank you very much and ask for any questions you might have.
Questions, Cecile?
Here.
Oh, sorry, we can't see much from up here.
It's very difficult.
Now, this is so exciting. I want to ask you, there is a project to send nano spacecraft by lasers pushing the sail to Alpha Centauri. It was not discussed here yet.
Right. So
Can you repeat this question, please?
If the nano
I just want to be sure that the
spacecraft
microphone will capture so
can
that
be
we have
sent
that on
by
us.
laser pushing the sail to this planet.
So he's wondering whether or not you could have a spacecraft that is using laser technology to push the spacecraft towards this system. So Alpha Centauri is about 4 light years away. We're about 10 times farther than that. So the estimates that I've seen so far for how long it might take a spacecraft to get all the way to the TRAPPIST system range from hundreds of thousands of years to longer than that. And that's ranging using spacecraft like laser technology, as well as some of the amazing spacecraft that have been designed in series such as Star Trek and Star Wars and such. So I think for a spacecraft to actually get out to TRAPPIST is certainly outside of our lifetime, but it's certainly an interesting idea.
But to Alpha Centauri, it took only 20 years and 5 times slower than light. How is possible?
So I'm going to have to refer you to really the engineers that have the technological background in the spacecraft technology. My background is quite a bit more on the astronomical side, but I have heard at least some discussion about trying to get a spacecraft with such technology out to Alpha Centauri, which also has an Earth-sized planet, at least one out there, which is exciting. Yes?
Hi. Can you comment on the activity of this star? Because it's an M star. And M stars are known to flare, have strong magnetic fields. You would think, of course, you should look for life on it, but you would not immediately think this is a star which is a very stable star.
So we have actually been looking at all of that information as well. We have caught some flares in the data that we've been looking at, and I've seen some papers as well that have been published that are question whether or not this is a particularly good system to detect life or not for just those reasons. And the answer is we don't know at this point until we point telescopes at and try to collect some data. But certainly we do know that there are places on the Earth that scientists absolutely discounted from the get-go as no possibility for life to exist in very extreme environments where we find life thriving. So I think this is a really ideal system to determine whether or not our understanding of life on the Earth could branch out and populate a planet around a star that is much more active and has high UV radiation and all of the things that seem to us to inhibit life. But it's always surprising to me where life flourishes, where we as scientists don't think is possible. So I think it's a lot of fun as a scientist to look at these things. And they even, prior to this, discounted M-type stars as a possibility for where planets could even form because the star itself is so small that certainly there's not enough matter to collect planets. So a system that has this many planets was a surprise, I think, to everybody, and really states that you can form planets around pretty much anything if you can form 7 around such a small star. Yes?
Well, I'm glad I deferred to that question because at Rice we're actually trying to model the magnetic interactions between like Proxima Centauri and also TRAPPIST. Mm-hmm. And so, the key thing is these are active stars. There's transient activity, but there's also just its generic stellar wind and so on. So how do you think we might be able to get a handle on the planets themselves have their own protection system if they have their own strong magnetic fields.
Right.
Is there any indications in some of this data that some of these planets might have such a strong magnetic field, or is it just guesswork at the moment until we can get radio observations or something?
Yeah, so that's an excellent question, and it lends back to the question that they had for Liz about, the magnetic field of Mars and how that was lost. And you can see from the sizes that the sizes of these planets vary quite a bit, and the bigger planets, of course, just like the Earth, have much more rock and such that help to insulate the warm interior for a potential magnetic field. But at this point, the data that we don't have data currently that has any indication of what the magnetic fields of the planets might be. So the data that we have really is strictly limited to the transit spectroscopy and the photometric transits. But that's definitely something that's being discussed in papers and by people because of this possibility of they're in the habitable zone, but around a star that's outside of our knowledge of whether or not life can form and what are the upsides and the downsides of that for life forming around these particular planets.
Right, and I think that's what we're trying to do with this magnetospheric modeling. If you don't mind, I would comment on the spacecraft. So it's a needle spacecraft, and it's like the size of a chip, so it's not exactly the one that's going to Alpha Centauri. So they're hoping to get 20% of the speed of light, but it's not going to have a lot of sophisticated instruments. It may have a little camera. And so that was just a comment on what you said earlier. Thank you.
So I appreciate your expertise on that for sure. Thank you very much.
I wouldn't call it expertise, I just know what I know.
Very good. To be dangerous. Thank you. Hopefully we've conveyed some of the excitement from robotic exploration and telescopic observation of the solar system. And I'd like to just thank all of our speakers again. Please join us. Thank you all. Thanks, Brian.
I'd like to thank Dr. Proctor and the entire panel for a very exciting and fascinating look at the future of exploration and what we've learned in such a short period of time. We're going to adjourn for lunch. It's a buffet lunch, but I'd like to have you back at 12:45. We're going to have the privilege for about a 10-minute presentation from Mr. George Abbey, who's a senior fellow in public policy for space at the Baker Institute of Public Policy, before we pick up with our 1 o'clock presentation from Dr. Kate Rubins on sequencing DNA on the International Space Station, followed by a very special panel of astronauts who are in next careers involved in space, both from a government side, from founding private corporations, and from advocacy. And we also, one of those is involved in plasma rockets and might help answer the question about transit times as well as Dr. Chang Diaz. So thank you very much. Hope to see you back in here at 12:45. Hey, thank you.